Hello there, welcome to Umid Private High School online class. In this class, I'm going to explain some remaining topics of 11th grade physics. And today's topic is potential energy. Potential energy is the energy due to height of object. Okay, so it depends on height. If height is more, potential energy will be more. If height is less, potential energy will be less. Okay, let me show you the formula also. This is the formula, and this diagram shows as the potential energy. You see, this object with mass m located at some height from ground level. At this height it is located, so it has some potential energy according to this level. Okay, so we can say that if height is more, potential energy will be more. If height is less, potential energy will be less. Height increase, potential energy increase. Height decrease, potential energy decrease. Okay, now let's see the formula. Potential energy, EP, means potential energy equal to mass of the object into gravitational acceleration of Earth into height of object from some reference level. So potential energy will be equal to m times g times height. M, you know, mass; g, you know, gravitational acceleration of the Earth; h, you know, height of object from ground or some other reference level. Okay, so let's solve a few examples to make it more clear. Example number 1, calculate the potential energy of the kite. Okay, here kite is given with mass 200 gram. 200 gram is it's equal to 0.2 kilogram. Okay, height from ground also given as 30 meters. So here we need to calculate potential energy. Potential energy is equal to m times g times height, h, and mass is given as 0.2 kilogram into g, you know, 10 Newton per kg, times height, here it is 30 meter. Okay, now kilogram, you see, kilogram cancel. The remaining terms will be 0.2 times 10 will be 2 Newton. Here we have Newton times 30 meter, and finally it becomes 2 times 3 6, and becomes finally 60 Newton times meter joule. So potential energy is equal to 60 joule. Okay, you see here one path is given like this and one height is given like this. Now let's see one important note about this. You see, this note says that potential energy does not depend on path followed. It depends only on initial and final values of height. Okay, so it does not depend on the path followed. Example number 2. Calculate the potential energy change. Okay, here we need to calculate delta PA. Delta PA. Changes in potential energy. You see here, initially height was 10, now height is 4. If height changes, potential energy also changes. Here we are going to calculate changes in potential energy. Okay, you know delta means change, right? So from here delta PE is is equal to final potential energy minus initial potential energy. Okay, final is energy here. Initial means energy of the object at this height. Okay, so from here m times g times m times m times g times h2. Okay, h2. Why? Because final energy is energy of object at this height minus m times g times h1. Why h1? Because initially object was here at this height, so initial energy will be due to this height. Okay, from here mass, you know, it is 3 kilogram. 3 kilogram times g, you know, 10 Newton per kg times height 2 is 4 meter minus m, you know, doesn't change, it is again 3 kilogram times g is 10 Newton per kg times initial height was 10 meter. From here this part becomes how much? Kilogram cancel, 3 times 10 30, 30 times 4 120 joules minus this part will be kilogram cancel, 3 times 10 30, 30 times 10 300 joules, and finally change in potential energy will be 180 joules. And it's minus. This minus shows that if height decreases, then potential energy will decrease. So changes in potential energy is 180. This minus shows the decrease in potential energy. Okay, conservation of mechanical energy. There's, you know, the concept of mechanical energy, right? Mechanical energy is kinetic energy and potential energy. We can say that mechanical energy is the summation of kinetic energy and the potential energy of a system, right? So here we study conservation of mechanical energy. It states that the total mechanical energy of an isolated system always remains constant. It means that the summation of potential energy and the kinetic energy of an isolated system always remains constant. Okay, now let's take this example. This object is at level A. Okay, it is at level A. At level A, it is at rest. Okay, it is at rest. At rest means velocity is 0. If velocity is 0, then kinetic energy will be how much? It will be obviously 0. Okay. Now let's see this table. You see kinetic energy is 0 at level A. What about potential energy? This object has one potential energy. How do we know it has potential energy? We know because it has one height from the ground. If it has height from ground, then it has one potential energy. Let's assume it has 100 joule potential energy. Now, if we add this potential energy and this kinetic energy, it becomes total mechanical energy of this object. Okay, then mechanical energy of this object is 100 joule. Now let's release this object. If you release this object, as it moves downward, its velocity increases. If its velocity increases, kinetic energy increases. Okay. Now let's assume at level A, at level B, the kinetic energy reaches to 20 joules. But what will happen to potential energy? You see, as it moves downward, height is decreasing. If height decreases, potential energy also decreases. Okay, kinetic energy increased by 20, potential energy decreased by 20, and finally it became 80. But if we add potential energy and kinetic energy, it becomes mechanical energy. Again, it is 100. 20 plus 80, 100. 50 plus 50, 100. 15 plus 85, 100. So it means that the total mechanical energy of an object or an isolated system always remains constant. Okay, let's solve some examples related to this concept. Example number 3 in this chapter. What is the velocity of the object as it hits the ground? Okay, just before hitting the ground, how much will be its velocity? Initially velocity was 0. Just before it hits the ground, its velocity will be how much? Okay, here we need to use the concept of conservation of mechanical energy. Energy at this level, okay, energy at this level, let's say initial energy should be equal to energy at this level. Okay, let's say final energy. Okay, according to conservation of mechanical energy, this initial energy should be equal to final energy. Okay, now let's use this concept. Initial energy should be equal to final energy. Here at this level we have two different energy, one potential energy, another kinetic energy. Okay, then initial kinetic energy plus initial potential energy should be equal to final kinetic energy plus final potential energy. You see, at this level kinetic energy is 0, then this expression becomes 0 because initial velocity is 0. Okay, now potential energy at this level will be m times g times h, should be equal to kinetic energy. Here object has kinetic energy, just before hitting the ground it has maximum kinetic energy, so you know the formula of kinetic energy, V square. And potential energy will be 0 at this level because height becomes 0. If height is 0, potential energy is 0. Okay, you see here we have common factors, mass cancel. Okay, now we solve for the remaining expressions. G, you know, 10 Newton per meter square, 10 Newton per kg, right? 10 Newton per kg times h, you know, it is 500 centimeter, but we should write n meters, it becomes 5 meters, right? This 5 meter, 5 meter should be equal to 1 over 2 times v square. Left side it becomes 50. Okay, 50. If we do cross product times 2, it becomes 100, right? Then 100 Newton meter per kg is equal to V square. Here, if we use Newton's second law here, okay, then this expression becomes 100 meter square divided by second square will be equal to V square. Okay, after using Newton's second law. Here, if you take under root, then V becomes equal to 10 meter per second. Okay, this is how we use conservation of mechanical energy. Example number 4. A ball of mass 200 grams is dropped from a height of 20 meters above the ground as in figure. Okay, from this point it is released. Okay, it is dropped and height is 20 meters. Okay. First, part A. Find the speed of the ball just before it hits the ground. Okay, before hitting the ground here, we should calculate the speed. Okay, so again, we need to use concept of conservation of mechanical energy. Energy at this point, let's say initial energy or energy at point A, should be equal to energy at point B. You see, this point is B. Now, these two energies should be equal according to conservation of mechanical energy. Okay, A or energy at point A is equal to energy at point B. Energy at point A, here we have two different energies, right? Kinetic energy and potential energy. Initial kinetic energy plus initial potential energy should be equal to final kinetic energy plus final potential energy. Final means at B. You can say potential energy at B also. Okay. Now, kinetic energy at point A. Here, kinetic energy is 0. It is 0. Only M times G times H A. Okay, height of point A should be equal to kinetic energy is 1 over 2 into M into V B square. Velocity of object at point B. Potential energy at this level is 0, so this one also equal to 0. Okay, again, you see common factors cancel, mass cancel. Remaining expressions will be G is 10 Newton per kg times height of point A is 20 meter equal to 1 over 2 VB square. Okay. Now left side you see it becomes 200. It is 200. 10 times 20 is 200. And after doing cross product, it becomes 400, right? 400 meters square divided by second square is equal to VB square. Okay. If we use Newton's second law, it becomes meter square divided by second square. Right? From here, if we take under root, velocity at point B becomes equal to 20 meter per second. And this is how we use conservation of mechanical energy. Dear students, for the solution of B part, I erase the board. Okay. Now B part.